What I would like to do in the next 25 minutes, I would like to take you through the journey from discovering a new API to finally making it in the desired form at the right quality consistently. So salvias, I trust and I hope everybody knows us, but for those few of you who don't, we're a contract research organization with what I would say a pharma pedigree, because we were formed 13 years ago as a management buyout from a big pharmaceutical company. We are obviously completely independent now, and our emphasis is analytics. Then there's my department, solid state, and plus we have a synthesis and catalysis department. We're about 250 people and are located, this is our new location here in Kaiseraugst near Basel, and we have another location in Basel itself. So when, as you know, of course, about the majority of drugs on the market are on the market as solids, and that means you have a vast array to choose from. You could market the API as such, as a pure molecule, and then of course you have there's the possibility that it can exist in different polymorphs. You could use the amorphous form. It might form solvates or hydrates. You might be able to make co-crystals of your API, and of course there's also the possibility to make salts, as I'm sure you know about. Almost half of the drugs on the market are on the market as salts. And then obviously you can also have polymorphs of solvates and hydrates. You can have polymorphs of co-crystals and of salts, etc. So there's an absolutely vast selection you could choose from as your final drug product, and which presents a huge opportunity, but of course which at the same time also presents a very big challenge. Because first of all, you have to identify from this myriad of forms all relevant ones, and then naturally you have to find out which is the best one for your application, for your process, and then finally you have to produce it reproducibly and cheaply. And naturally what we can do at Salvias, we can sort of guide you through this whole process. We can find the forms for you, we can characterize them and select the best one for you, and we can make it for you. And in order to be able to do that, a lot of people say they can, but I think to do it well, it's really essential to have know-how, to have experience, and naturally also need the equipment for it. So what is the homework you have to do in order to end up with your best product reproducibly and cheaply? First of all, you have to find out if you're not completely happy with the API as such, is there a better salt or co-crystal? So you have to screen for salts and co-crystals. Then once you've decided on salt, co-crystal or API as such, you have to find out, does it form different polymorphs, does it form hydrates, solvates, etc. So you have to screen for polymorphs. And then probably the most important thing is you have to understand the properties of these various forms. You have to characterize them well. You have to understand the transition from one form to the other, so that you can really then select the best one, or which is the best one for your particular application. Then after that, you have to develop a crystallization process to make that desired form. And then of course you have to transfer it to a GMP facility to produce it under GMP. So let's start with salt co-crystal screening. First of all, why would you go for a salt or a co-crystal? You would go for a salt or try to go for a salt or a co-crystal if you're not 100% happy with the properties of your neutral molecule as such. And what you might not be happy with, of course, would be number one problem would be solubility. Could also be that it's difficult to crystallize the neutral molecule, or that it has other undesirable properties like low melting point, etc., which makes it hard to formulate. So in other words, you're then looking for a salt or co-crystal which has a lot of good properties or where a lot of properties are optimized, such as crystallinity, such as solubility. You want to have something which is not hygroscopic. You want to have something which is stable, which is easy to process, and which also doesn't have what I call here problem solid forms, which could be, for example, enantiotropic polymorphs with a transition temperature near room temperature, which could be channel hydrates, etc. So in other words, you want to optimize lots of properties at the same time, which means immediately that it's definitely recommended that you do a broad salt or co-crystal screen. The hydrochloride or the sodium salt might not be the optimal one, so you have to look at lots of different salts and then find the optimal one. Next thing would be polymorph screening, then where you look for the polymorphs, various solid forms of the salt, co-crystal or neutral molecule, and there the key is really diversity. I mean, the principle of a polymorph screen is that you use different supersaturations, different solvents to explore the whole parameter space of crystallization. And so, as I said, their key is diversity. And a very good tool for polymorphism screen, and I want to emphasize it's only one tool, would be a robotic high-throughput screening. We recently acquired such a Chrissy robot from Zinser, and we acquired that because Zinser was happy to make a lot of modifications in that screening apparatus according to the best practices we had developed over the years previously. So on that high-throughput screening, we can then analyze the solids which are formed on such 96 well plates. We can analyze them both with powder X-ray and Raman, which gives us optimum specificity and sensitivity. And the instrument allows us to use a variety of crystallization techniques which create various supersaturations, such as slurries for a very low supersaturation. We can also filter hot slurries, which is very powerful. We can do cooling crystallizations, we can do evaporation, we can do precipitation. So we can use the whole gamut of crystallization methods in solution. And I said it's only a tool. Of course, we complement that with other crystallization techniques like crystallization from the melt, or maybe sublimation, effect of pressure, etc. So in such a screening, you identify new forms which are potentially interesting. And then, of course, the big thing is to understand these forms, to understand their properties in order to be able to select the best one. So what do you want to know? What do you want to characterize of these forms that you find? Of course, you want to know solubility, you want to know stability, hygroscopicity, habit can also be important. For the polymorphs, you certainly want to know thermodynamic stability. Are two polymorphs, are they enantiotropic, are they monotropic? If they are enantiotropic, what is transition temperature? What is the solubility difference of the various polymorphs? Then hydrates, of course, play a very big importance. Again, as I'm sure as you know, normally you would select for your final drug product, you would select either the stable polymorph or a hydrate. So if hydrate formation is possible, you really need to understand their thermodynamics and kinetics. You need to understand critical water activities, conversion rates, etc. And finally, solvates, while they are not important for the drug product, there are a couple of drug products on the market which are solvates, but only about 2. But of course, it's important to know if solvate formation happens, because these are the solvents you want to avoid for the crystallization process. So just one example, I mentioned thermodynamic stability. If you have two polymorphs, they can be either monotropic, where one form is more stable than the other at all temperatures, or they can be enantiotropic, where there's a transition temperature. And here is an example where we calculated such a quantitative energy temperature diagram using data that we got from DSC measurements, such as melting points, melting enthalpies, and heat capacities. And what you can see here is the free energy of form 1 and form 2. as a function of temperature, and you can see the free energy of these two forms cross over at a temperature of about 75 degrees centigrade. So this would be a case where we have two enantiotropic polymorphs, and with a transition temperature which is important for your crystallization process. We see here is 75 degrees, so that means immediately it's probably advisable to start the crystallization at a temperature lower than 75 degrees. Or if you start the crystallization at a higher temperature, you have to take care that there's no form conversion during the crystallization. Such a transition temperature, which we would calculate here from thermal data, we would then of course also verify it with slurry experiments at various temperatures to make sure that 75 degrees is the exact temperature. So from such a characterization you learn a lot about, first of all, which form to choose, and secondly you learn things about how you should carry out your crystallization process later. Second thing would be hydrates. I already said that before. Hydrates are particularly important because they are often used as the final form in a drug product. And here I have a phase diagram of a substance which can form two different hydrates. So you have here in the phase diagram the stability region of the anhydrate, here that of the monohydrate, and here that of the dihydrate. And the important thing about hydrates, at least for stoichiometric hydrates, is that the transition between hydrate and anhydrate is a sharp, stepwise one, as depicted here. So there's only one particular water activity or humidity where hydrate and anhydrate are in equilibrium, and if it's a little bit lower, only the anhydrate is stable, a little bit higher, only the hydrate is stable. And of course, such a phase diagram, or knowledge of such a phase diagram, again, is crucial when you want to develop the crystallization process to make the desired form. Say, for example, in this case, we had chosen the hydrate as the form for development. Then we would have to make sure that during the crystallization process, we always stay in this yellow region of the phase diagram to make sure that we get the hydrate consistently and reproducibly. So, in other words, it's important to know critical water activities, to know phase diagrams or determine them. How do you do that? The easy experiment for hydrates would be a DVS, or dynamic vapor sorption experiment, for those of you familiar with it. There you just change the humidity and then measure the mass as a function of humidity. And if hydrate formation occurs, you often see a stepwise increase at a certain humidity. When you go back, you see a hysteresis and a decrease. The message here is, this is not a good way to determine the critical water activity because you don't know where the critical water activity is. It could be anywhere within that region, and often the region is much, much broader, or you don't even see a conversion. So how to do that? How to determine this all-important parameter of critical water activity? What we do, how we do that, we also do that in a high-throughput kind of manner, where we slurry a mixture of hydrate, solid hydrate and anhydrate in water-solvent mixtures of various water activity in such a well plate, and then determine what form wins at the end, because at a certain activity, always either the hydrate or the anhydrate will win. And then you get an exact value for the critical water activity. So example depicted here. In this case, this substance could form a hemihydrate and an anhydrate, and you see here Raman spectra of these forms, and you can see here the typical peak of the hemihydrate. And if we now slurry mixtures of hemihydrate and anhydrate at various water activities, you can see at 0.9 and 0.8 the hemihydrate wins, and below 0.7 and below the anhydrate wins. So obviously the critical water activity here is between 0.7 and 0.8. You also have to determine that at various temperatures. depicted here. And so by doing that in a high throughput way, we get the phase diagram and can then determine crystallization parameters. In this particular case, we helped the customer who produced mixtures of hydrate and of anhydrate and hemihydrate, and we then told them how to change the conditions to get the desired form, which was the anhydrate consistently. Okay, so then once you've selected the optimal form, you have to find a way to crystallize it. And if you look at the solubility curve of any substance, then normally solubility increases with temperature. If you cool down a hot solution, then of course it normally won't crystallize at the same point where it dissolves. There will be a metastable zone, after which it crystallizes spontaneously in the unstable zone. You get this metastable zone width. Now, if there's a second polymorph, the situation will look like that. It will have a different solubility as a function of temperature. And now, if you cool down a hot solution and you don't use any seeds, your system won't know what to do, whether it should go in the direction of polymorph B or A, and so you might get mixtures of A or B, or you might get A today and B tomorrow. So I think it makes a lot of sense that you should always use seeded crystallization processes, because then you can seed with the desired form, you template the desired form, you can also control particle size, etc. So in a seeded process, of course, you start with a hot solution, you cool down to the metastable zone range, and then in the metastable zone where you don't have spontaneous crystallization, you induce crystallization with seeds, and then you cool down slowly, making sure you always stay in the metastable zone. This way you ensure that you get the right polymorph, and you can also control the crystal size. And of course, what you have to optimize in such a seeded process is then seeding temperature, cooling ramp, amount of seeds, etc. And the way we do such an optimization, we do that normally with a metal multimax equipment with a Lasentec probe. Lasentec probe counts particles and measures their size, so that's ideal for a seeded process where you, in principle, want the particle number to stay constant and you want the particles to grow. And of course, with that equipment, we have optimal control over the crystallization process. We have small test tubes for metastable zone width equipped with turbidity probes, and then larger vessels with proper stirrers which simulate the crystallization process very well, with these parameters I mentioned before to optimize. And then next important step obviously is to scale that up and transfer it to a GMP environment. And we have a GMP kilo lab at Salvias where we can then, using 160 liter vessels, where we can then produce a few kilos of the desired polymorph for you. And for a successful scale up to this 160 liter scale, of course, very efficient know-how transfer is essential. And these couple of kilos could then be used either for phase 1 or 2A, or they could be again used as seeds for a CMO to make hundreds of kilos of GMP material. So to end up with, I will just walk you briefly through a case study where we did such a development, where we did quite a large part of such a development, where the objective of our customer was to find a new solid form of a certain API for IP reasons. I think an issue that a lot of you are familiar with. So what we did is we did a co-crystal screening there, trying to find new co-crystals of the API. After that, we did characterization of the co-crystals. We found a good co-crystal. We developed the crystallization process for that co-crystal, and we made multi-kilo amounts under GMP of that desired co-crystal. So let's start with the screening. We did screening again in a 96-well format, where we screened for 24 different co-crystal formers. which were selected from the grass list and from the everything added to food list. Result of that screening was that we found leads for several co-crystals. One lead for a carboxylic acid co-crystal was particularly promising. Next step was then to scale up this co-crystal from the milligram scale in this 96 well plate to the 100 milligram scale and further characterize it. And here you can see Raman spectra. First of all, you can see here why this co-crystal in the high throughput screening was determined as a lead. You can see here the co-crystal in the Raman spectrum with the Raman microscope of the co-crystal in the high throughput screen. And this solid had lines from both the co-crystal former and the free drug, but they had shifts in the lines, so that was a good indication that co-crystal formation had taken place. The scaled up co-crystal to 100 milligram then had the same Raman spectrum as the 1 milligram co-crystal in the high throughput screen, telling us we had made the same. And we then characterized these 100 milligrams, and it had good properties, had quite a good morphology, had a higher melting point than the original form, which was very positive because the original form had a melting point of about 80 degrees, which is always a problem for tableting. It was stable, etc. So we then scaled up from 100 milligram to a proper 250 milliliter process using that metal multimax with the Lasentec probe. We used here, that's the solvent, seed amounts, etc. that we used. And this way we were able to devise a crystallization process to successfully make these co-crystals on the 100 gram scale, which was then further transferred, as I said before, to our GMP kilo lab, where we could then successfully make 2 kilos of this co-crystal under GMP. So with that, I would like to conclude, and I'm even on time. So I think if you do your homework, it's a lot of homework that you have to do, but it really pays off because you'll have a better product in the end. You'll have a better process, a faster, more efficient, safer, and probably also cheaper process in the end. So it's certainly worthwhile putting in that effort. But in order to really be able to reap all these benefits, it's really essential that the company or the CRO you're working with really has the in-depth knowledge of this whole process from screening to crystallization development. And I think I can definitely say that at Salvias you can have access to that knowledge. So summarizing, I think at Salvias we've done many projects of this kind. We have an outstanding track record. We have a part, of course, from the capabilities I mentioned here in solid state. We have a vast array of comprehensive capabilities for chemical and analytical development. We have a strong technology base, and I think we are really obviously dedicated to meet timelines. We're quick and we are efficient. And with that, I would like to thank you for your attention. You could also visit us at our booth in Hall 8 and welcome any questions you might have. Thank you.